Hello everyone, today we are going to take the topic, the name of the topic is limits, useful for 11th and 12th standard for all state boards, CBSE examination and ICSE examination, as well as it is very useful in BSc computer science as well as engineering examination as well as GATE examination. So this concept is required everywhere in this mathematics. It is a part of the calculus. Now we are going to understand first the difference between actual value of the variable and limiting value of the variable. If I take for example x equal to a and if I take for example x tends to a, so we will understand the difference between these two statements. Here this is pronounced as x tends to a. We are going to show this in the form of an arrow directing towards the constant value. X is a variable and a is constant. To understand this concept in detail, let us take for example x equal to 5. So we can say that value of x is exactly equal to 5, and then here we can take x is equal to 4.99998 and let us take x is equal to 5.000012. Now what is the difference between these two? In both the cases value of x are very near to 5, but it's not exactly equal to 5. So we can say that x tends to 5, and here also we can say that x tends to 5. In both the cases value of x is as good as 5 but not exactly equal to 5. More precisely, this can be written as 5 minus and 5 plus. What do you mean by 5 minus? That is value of x is as good as 5 but just less than 5, and meaning of 5 plus is that value of x is as good as 5 but slightly greater than 5. And here we can say that in general x tends to a minus or x tends to a plus. Whenever we write down x tends to a minus, we can say that it is a left hand limit. Left hand means in the negative side, and when we say that x tends to a plus, that is called as right hand limits. So this is the difference between left hand and right hand limits. So this is the concept regarding the meaning of tending to. X tending to a means what? That I have explained with the example of x equal to 5 and x tends to 5. So this is the difference between actual value and here value which is approximate. Now let us consider any function, for example f of x, and if I want to find out the value of function at particular value of x, that is a. So if we say that x equal to a, then here we get f of a as the actual value of the function. So this is actual value of the function, means value of the function when x is exactly equal to a. But if we want to find out limiting value of the function, then what you are going to do? Here if x tends to a now, so if it is x tends to a, even though you are going to replace this x by a, but now here whenever we take x tends to a, this is not called as actual value, this is called as limiting value of the function. And when the limits exist or when the limit does not exist, whenever we take x tends to a, then the value of the function at both the limits, means when x tends to a minus and when x tends to a plus, must be same. For example, if I write down limits as x tends to a, f of x must be equal to limits as x tends to a, f of x. More precisely, I am going to take this as a minus and a plus. So whenever this condition satisfies, we say that limiting value of the function exists, and actual value means we just have to put x equal to a. Now whenever we are going to put x is equal to a as the limiting value, you may have to do certain algebraic adjustment to get the limiting value of the function. Now limiting value and actual value, the concept is required to understand the concept of continuity. That continuity we will take in our other video whenever we take in future. So time being, you just have to remember that is f of x as x tends to a minus or f of x as x tends to a plus, the whatever value we get, and that value is called as limiting value of the function. Now we are going to take algebra of limits. Now for understanding algebra, let us consider two functions. One is f of x and other is g of x. Whenever we are going to take limits while doing algebraic operations, these rules must be followed. Number one, limits as x tends to a, f of x plus or minus g of x. So whenever there is addition or subtraction, first of all you are going to separate two functions in this manner. So limits of x tends to a, f of x plus or minus limits as x tends to a, g of x. Whenever there is multiplication or whenever there is division, again we are going to follow the same concept. We are going to separate the functions and then only you can take the limits. So here limits as x tends to a, f of x, limits as x tends to a, g of x whenever there is a product of two functions, and whenever there is a division of two functions, again limits are to be separated. But important condition here in the division, that whenever you take the limits, particularly for gx, that denominator should not be 0, otherwise it will be not defined. And whenever there is a product of constant term with the function, first of all you are going to take that constant term outside and then only we can take the limits. Now exactly if you want to find out the limiting value, what you are going to do? Here I already told you that limiting value means x approaches a, x is not exactly equal to a but it is as good as a. So for example, here if I want to find out limits as x tends to a, f of x or x tends to 2 I will take, just to understand, and then we can take limits as x tends to 2x square plus 9. So what exactly you are going to do? You just have to replace value of x equal to 2. So here we get 2 square plus 9 and that is equal to 13. So we can say that 13 is the limiting value of the function. Whenever x tends to 2, and whenever x is tending to 2 means value of x is as good as 2, value of the limit is as good as 13. Whenever there is a limiting value, in that case value of the function is not exactly equal to 13 but it is as good as 13. So this is the concept, the meaning of x tends to and limiting value of the function. Now in our next part we will find out how to solve the examples of the limits. Let us proceed for the topic limits of algebraic functions. Here we are going to use this formula. This formula can be derived using the concept of binomial expansion. So we are going to take the proof of this formula in the chapter of binomial expansion. So formula is like this: limits as x tends to a, x raised to n minus a raised to n upon x minus a is equal to n into a raised to n minus 1. So whenever this type of situation is there, we can write down the answer directly. For example, if we are having limits as x tends to 3 and if you are having x raised to 4 minus 81 upon x minus 3. So this can be solved directly using that formula. It can be proceeded in this manner: limits as x tends to 3. Now you know that 3 raised to 4 is nothing but 81. So we can write down x raised to 4 minus 3 raised to 4 upon x minus 3. And now this example is exactly in the form of standard formula where value of a is 3 and value of n is nothing but 4. So we can use that formula straight away. So write down the final answer as 4 into a means 3 and raised to n minus 1. So 4 minus 1 is nothing but 3. So here we get 4 into 27 and ultimately we get final value of this example as 108. So 108 is called as limiting value of the function. Means whenever value of x is as good as 3, then value of the function is as good as 108. So this is called as limiting value of the function. Now let us understand one more concept. Here for example, if I take limits as x tends to a, if you take numerator for example as x square minus a square upon x minus a, in that case if you put straight away x equal to a in this, then you will find out we get this example in the form of 0 upon 0, and 0 upon 0 is called as indeterminate form. Indeterminate form means that value we cannot determine, and therefore this is termed as indeterminate form or value which we cannot determine. So whenever there is an example, first of all we have to check whether it is in the form of 0 upon 0 or not. If it is 0 upon 0, then in that case either you can use this formula, but when this formula is not applicable, then you can do certain adjustment like factorization to solve that, and you have to ensure that it is not in the form of 0 upon 0, and then only you are going to put the value of x as a. So this is the concept of the indeterminate form. Now we will take various examples to understand of this indeterminate form as well as how to find out limits of algebraic functions. Let us take now two examples to understand the concept of limiting value of the function. First example is limits as x tends to 2, x square minus 5x plus 6 upon x minus 2. If you put x equal to 2 directly, you can observe that we are getting denominator as 0, and if you put x equal to 2 in the numerator, again you can observe we are getting 0 in the numerator, means it is in the form of 0 upon 0, and that is called as indeterminate form. So while solving the example, you have to simplify it further. You cannot put the limits directly. So how it can be solved? Standard formula is not applicable, and therefore we have to try the factorization of numerator. Denominator is a single term, but numerator is a quadratic term, and then we have to factorize. Limits as x tends to 2. We can say that we can factorize numerator in the form of x minus 2 into x minus 3 upon x minus 2 as it is. And since remember that whenever you do the calculation, we cannot cancel 0 upon 0, but here value of x is tending to 2. It's not exactly equal to 2. If it is exactly equal to 2, then it becomes 2 minus 2 0, 2 minus 2 0. We cannot cancel that. But here you have to remember this concept as a value of x tending to 2. X minus 2 is tending to 0, is not equal to 0, means we are not cancelling 0 upon 0. This is very important concept that you have to remember, and whenever you write down in your final examination, then you are supposed to write down this step, that is as x tends to 2, x minus 2 is tending to 0, means it's not exactly equal to 0. In other words, these two brackets are non-zero term, and that's why we can go for cancellation. Limits as x tends to 2, and here we can write down x minus 3 because these two brackets are cancelled, and now we are in a position to put the value of x as 2. So 2 minus 3, and we are getting limiting value as minus 1. So whenever value of x is tending to 2, value of the function is equal to minus 1, or it is as good as minus 1, not exactly minus 1, and this itself is called as limiting value. Let us use now the same concept for solving the second example. Second example is now limits as x tends to minus 2. Numerator is minus 2x minus 4. So we can try orally. If we replace x by minus 2, here we are getting 4 minus 4, and that is 0. You can also check in the denominator. Minus 2 cube is minus 8, and plus 2 into minus 2 square. So it is 4 into 2 8, and 8 minus 8. Again we can observe it is in the form of 0 upon 0, means it is indeterminate form. So you cannot put the value of x directly. So we need some adjustment. So what adjustment that you can do here, we will do one by one. So that is equal to limits as x tends to minus 2. So from numerator it is better to take minus 2 common. So in bracket we can write down x plus 2. And from denominator let us take x square common. So in bracket we get x plus 2. Again we have to use the same concept as value of x tending to minus 2, x plus 2 is tending to 0, it is not equal to 0. So x plus 2 is a non-zero term, as x tends to minus 2, and therefore we can cancel that x plus 2, and therefore we can write down limits as x tends to minus 2 upon x square. And now we are in a position to take the limits. So here we are taking the limits. If you want, you can write down here in a statement form, that is taking limits. If you don't write down, okay. So taking limits. So we get minus 2 upon minus 2 square. So minus 2 upon 4, and therefore we get limiting value of the function as minus 1 by 2. So what do you mean by limiting value? So when value of x approaches minus 2, when value of x is not exactly equal to minus 2, in that case value of the function is approaching the value of minus 1 by 2. So this is the concept of limits of algebraic functions that we have studied. We have taken a standard formula and we have solved 2 examples based on this limits of algebraic function. Now we will proceed further for understanding the limits of trigonometric functions. Let us proceed for new topic, and that is limits of trigonometric functions. Now in limits of trigonometric functions, we are going to use the formula limits as theta tends to 0 sin theta upon theta is equal to 1. This formula is applicable only and only when theta is measured in radians and not in degrees. Always remember one point: whenever we do the calculation in topic calculus, then theta must be taken in radians. What do you mean by calculus? Which topics are involved in calculus? That is limits, continuity, derivatives, integration, differential equation, etc. So whenever these topics we are studying, remember that theta must be expressed in terms of radians and not in degrees. Now we will see that this is the basic formula. So we can modify this formula so that in competitive examination or in multiple choice question examination, then we will be able to solve the example in minimum time. So which formulas can be used? Limits as theta tends to 0 tan theta upon theta is equal to 1. This formula can be used. Now why this formula can be used, that we will see. Sin theta upon cos theta is equal to tan theta, that you know. So if you replace tan theta by sin theta upon cos theta, then this expression will take the form limits as theta tends to 0 sin theta upon cos theta upon theta. And then further it can be written as limits as theta tends to 0 1 upon cos theta multiplied by limits as theta tends to 0 sin theta upon theta. Now it's very clear from this particular separation that 1 upon cos theta is always equal to 1 as theta tends to 0, and sin theta upon theta equal to 1, and therefore tan theta upon theta as theta tends to 0 can be written directly as 1. Next we can take limits as theta tends to 0 sin of m theta upon theta can be written directly as m. Means if there is a multiplication of theta by any constant term, then that is answer. Now why it is so? Again we can check that. So limits as theta tends to 0 sin of m theta, here I am going to multiply by m and divide by m. Now what is the difference between the term sin theta and sin of m theta? Both are one and same. Why? When theta tends to 0, then m theta also tends to 0. So whenever you are using the formula that sin theta upon theta is equal to 1, this angle approaches to 0. Now whether the angle is theta or whether the angle is m theta doesn't make any difference, because as theta approaches to 0, naturally m theta also approaches to 0, and therefore sin m theta upon m theta can be taken directly as 1, and then m can be written as it is to get the value of this limits as m, and therefore sin of m theta upon theta can be written directly as m. We can use the same argument for writing down the formula, that is tan of m theta upon m theta, or rather theta is equal to m. So tan of m theta upon theta is equal to m can be written directly. We can use this formula further in this manner. If I take limits as theta tends to 0, sine inverse of theta upon theta, we can use this concept once again. That is, let us assume that sine inverse of theta is equal to x. So ultimately we can say that theta is equal to sine x. You can also change the limits as theta tends to 0. What about x? You know that sine inverse of 0 is 0. So limits can be changed into new variable x tends to 0. And now we can put in this formula. So limits as x tends to 0, sine inverse theta is nothing but x upon sine of x. So whether you are writing down sine theta upon theta or x upon sine x, again it is one and same, because they are nothing but reciprocal of each other, and reciprocal of 1 is also 1, and therefore we can write down answer directly as 1. So we can remember this formula also, that is limits theta tends to 0, sine inverse of theta upon theta is equal to 1. And you can also use this formula, limits as theta tends to 0, tan inverse of theta upon theta directly can be written as 1. So these are the shortcut formulas that you can use while solving the examples. Let us take the example based on limits of trigonometric function. Limits as x tends to 0, 2 sin x minus sin 2x upon x cube. Again we can observe, if you replace x straight away by 0, then you will get this expression in the form of 0 upon 0. Means again it is in the form of indeterminate form, and that's why we need to do certain adjustment, then only we can use standard formula, limits as theta tends to 0, sin theta upon theta equal to 1. So what kind of adjustment that you have to do here? This is a purely a trigonometry example. So here we can write down 2 sin x as it is, and now we can see second term, it is sin of 2x. So sin of 2x can be expanded as 2 sin x into cos of x whole upon x cube as it is. And now we are going to simplify the term. So limits as x tends to 0, 2 sin of x in bracket 1 minus cos of x upon x cube. Now we know that sin x upon x is equal to 1, and therefore that formula can be applied and we can make it 1, and therefore we are going to split this particular limit into 3 parts. Why in 3 parts? Because as per our algebra of limits, 2 is a constant term, must be taken outside the limits, multiplied by limits as x tends to 0 sin x, and multiplied by limits as x tends to 0 1 minus cos x. Now we know the standard formula, limits as x tends to 0, sin of x upon x is equal to 1, and therefore this x cube can be splitted as x multiplied by x square. So value of the limit doesn't change, and therefore sin x upon x as x tends to 0 can be made straight away is equal to 1. Here we can take the limits at any step, means if the value of this particular term is finite, then we can get that value and we can write down that in the form of a multiplication. Now further, 1 minus cos x upon x square is to be solved further. Now there are 2 ways to solve it. Either you can go for rationalization of numerator, or second way is also there, and that can be half angle formula that can be used. So there are 2 ways after this how to solve further. I am going to rationalize the numerator. That is easy way of solving this example. So multiplying and divide by 1 plus cos x. So x square into 1 plus cos x. You can observe that numerator is now in the form of a minus b into a plus b, so it becomes a square minus b square. So further we can write down 2 into limits as x tends to 0, 1 minus cos square x, and upon we can write down x square into bracket 1 plus cos x. Whenever we simplify this, we always have to check if there are 2 terms in the denominator, which term is finite, and can be separated. So we can observe that 1 plus cos x, if we replace x by 0, we get 1 plus cos 0, and 1 plus cos 0 means we are getting 2 there, and therefore we are going to write down this expression in this manner. So 2 into limits as x tends to 0, 1 upon 1 plus cos x. And what about second? Limits as x tends to 0. Observe numerator now, it is 1 minus cos square x, and 1 minus cos square x is nothing but sin square x, and denominator is x square. So sin square x upon x square can also be written directly as sin x upon x whole square. Means by doing certain trigonometric adjustment, we are converting original expression into our standard formula, and then we are going to use the formula. So here we can write down now, that is taking limits. So here we are taking the limits. So 2 into 1 upon 1 plus cos of 0 multiplied by sin x upon x as x tends to 0 is 1, and bracket square as it is. Now we know that cos 0 is equal to 1, and therefore 2 upon 2 we are getting value of the limit as equal to 1. Let us take next example for limits of trigonometric functions. Limits as x tends to a, cos x minus cos a upon x minus a. Again we can put the value of x is equal to a orally. You will come to know numerator is cos a minus cos a, that is 0, and denominator a minus a, that is also 0. So again we can observe it is in indeterminate form. If we are going to use certain advanced method, then this problem can be solved literally using one step. But if this problem is in 11th standard, then you have to follow these steps, and the steps are like this. Let us assume that x minus a is equal to t. So I am teaching you one more method of finding out the limiting value, that is substitution. So x minus a is equal to t means we are going to change limiting variable. So as x tends to a, then if you replace x by a, we get t is equal to 0, and therefore we can say that t tends to 0. So value of t is now is equal to 0 or tending to 0, and therefore we get x is equal to a plus t. So we can substitute in this equation now limits as t tends to 0, cos of a plus t minus cos of a as it is, since it's a constant term, and denominator is now t. Again I would like to tell you, if you are in 12th standard and if you already learn the concept of L'Hospital's rule, in that you can find out the answer of this particular example orally. We don't require these steps. These steps are to be followed if you are going to solve this example in 11th standard. Now hereafter there are different ways of solving it. Either you can use the formula of cos c minus cos d, or we can also use the formula of cos of a plus b. Better to use the formula of cos c minus cos d. The formula is, that is minus 2 sin of c plus d by 2. So therefore addition of angle upon 2, minus 2 sin of c plus d by 2 multiplied by sin of c minus d upon 2. So this is the formula that you have to remember. We are applying the formula cos c minus cos d, that is minus 2 sin of c plus d by 2 into sin of c minus d upon 2 whole upon, we can take t as it is. And now we are going to simplify it further. We can observe that this a and a gets cancelled, and therefore we are going to split this expression into two parts using the concept of algebra of limits, and that is equal to minus 2 is a constant term, must be kept outside, limits as t tends to 0, and we can write down sin of 2a plus t upon 2. That is the first term I have written. And then we can write down limits as t tends to 0, sin of t upon 2 upon t as it is. So this is the way of splitting the term using the concept of algebra of limits. Now this concept is already explain to you, if it is in the form of limits as t tends to 0, sine of mt upon t is always equal to m. So answer is always equal to coefficient of t. This is already explained to you in our earlier part. So we are in a position to take the limits. So here I can write down taking limits. So we get minus 2 multiplied by sine of 2a plus 0 upon 2. So we just have to replace t by 0 in the bracket. And as far as second term is concerned, it is in the form of sine of mt upon t is equal to m. So coefficient of t is 1 by 2, and therefore the answer of that limit is 1 by 2. So final answer is minus 2 into sine of a into 1 by 2, and therefore we get limiting value of the function as minus sine a. So this is all about limits of trigonometric functions.